Good morning. My name is Richard Baumer. I'm an assistant professor in the Department of Welding and Materials Joining Engineering at LeTourneau University in Longview, Texas. I'd like to thank DSI for the opportunity to present with you all work that we've done where we've coupled welding experiments with Gleeble thermomechanical simulations as a means of probing the relationship between welding process parameters and weldability or microstructure evolution in a particular advanced stainless steel. So today I'll begin by providing a brief overview of LeTourneau University, who we are and what we do, as well as an introduction to my home department, the Department of Welding Engineering, and then we'll finish that with a quick intro to the instrument that we used for part of this work, our Gleeble 1500. In the second part of the talk, we'll dive into the meat of it and probe specifically the relationship between welding process conditions and microstructure. This work came about through some initially surprising results that we didn't fully understand. We dug into the details of how welding drives thermal cycles and reheating in multi-pass welds that affects microstructure. And by the end, you'll see that it all builds a story that makes sense. And part of that relied on our use of both welding and Gleeble experiments where we actually reutilize welds. And then we'll offer some conclusions and look forward to your questions. So first, a quick introduction to LeTourneau University and the Department of Welding and Materials Joining. So LeTourneau University was founded in 1946, 75 years ago, initially as a technical institute with a hybrid work-study model. Was founded by a well-known industrialist, R.G. LeTourneau, nearly 300 patents, including things like the motor-driven wheels for earth-moving equipment, rubber tires on earth-moving equipment, offshore oil platforms, many key industrial innovations, including building 70% of the earth-moving equipment utilized in World War II. Now, since the beginning, we've grown into a comprehensive university, still based in Longview, Texas, a beautiful campus, and we're really the premier Christian polytechnic university in the U.S. What that means is we offer a broad range of programs. We're primarily undergraduate, residential, with flagship programs in engineering and aviation, as well as numerous other degree programs, including things like nursing, business, full liberal arts, theology. We also have graduate residential programs in engineering and active work in mechanical, electrical, and welding engineering, as well as occasionally students in civil and biomedical engineering. We also offer a wide range of online programs, including undergraduate and graduate programs, such as Master's of Business Administration, counseling, etc. And our campus offers really excellent resources, as you'll see shortly. Here's a snapshot of one of our labs to do this kind of work. And what we're really known for are two things. First, we are a Christian university, and it's a vibrant faith community. It began as a meaningful core part of the institution's identity, and it remains that way today. And then the second is that we really believe that the best way to learn is to put theory into practice. And so we are rigorous in our instruction, but applied in our orientation. And we feel that that's the best way to learn. The Department of Welding and Materials Joining Engineering is housed within the School of Engineering and Engineering Technology, which is home to multiple ABET accredited engineering programs, including mechanical, electrical, biomedical, civil, and a wide range of engineering technology programs. Within the Bachelor of Science in Engineering and Bachelor of Science in Engineering and Technology general degrees, we have options to concentrate in materials joining engineering. At the graduate level, we offer a Master of Science and a Master of Engineering with a specialization in materials joining engineering. Our department's distinguished by four major things. The first, of course, is our academics. We are rigorous in our approach to teaching, but also cognizant of the need to put that theory into practice. We align our curriculum to the needs of industry and strive that every student that leaves is ready to make an impact on day one. Most of our students choose to go directly into industry, but because of the rigorous foundation that they receive, we often have students who have opportunities to pursue master's or PhD additional study at top material science and metallurgy programs throughout the US. We are focused on the hands-on, and what that means is that teaching and applied research happens in great modern laboratory environments where students really get to see how the principles that they're learning in class apply in the real world. This is really enabled by our strong connection to industry. We have an enthusiastic group of alumni that actively support what we do and make our curriculum better, our facilities better. And then finally, we are an authentic Christian faith community, and that plays out in multiple ways, whether it's professors beginning classes with a prayer and a devotional thought, or just making themselves available to be mentors to students. Students really have the opportunity to learn and grow as a whole person at LeTourneau University. So from a content standpoint in welding engineering, we strive to bring together four major things. And the first, of course, is engineering. Our students are learning to be engineers, and that goes all the way from the freshman engineering design experience through multiple courses to a capstone year-long senior project that we call senior design. And they're dealing with the design process as well as detailed engineering quantitative analysis, as well as topics like weld sizing and inspection of weldments. We're rooted and grounded in the welding and joining processes, which of course requires that we understand material science and welding metallurgy so that we can know the details of how different materials respond to welding and joining. And then finally, automation is just a way of life, and so students have the opportunity in our lab to work with that kind of equipment in various classes, as well as if they so choose to take elective courses in automation or robotics. Teaching and research happens in well-equipped laboratory facilities. Over the last 2 years, we've made significant investments, both as an institution and in partnership with multiple partners. We're really grateful to Miller Electric, Fronius, ESOB, and Lincoln Electric, as well as Trinity Rail, who have all helped equip a new welding science lab. This welding science lab is home to industrial grade equipment, all the major arc welding processes such as submerged arc welding, gas metal arc and flux core, gas tungsten arc welding, as well as robotic and mechanized welding equipment. We also have excellent welding education facilities. We have 16 welding booths equipped with current state-of-the-art multi-process welding power supplies. And we have additional space for fabrication. And finally, we have solid state welding capabilities, including direct drive friction welding and friction stir welding. In addition to our welding high bay, we also have great materials characterization facilities, standard optical microscopy and microhardness testing, sample preparation, as well as mechanized gas tungsten arc welding equipment, which was used for the work I'll be reporting later this morning. And then finally, a materials simulation and characterization lab, home to a new scanning electron tungsten filament microscope with EDS and EBSD, as well as a Gleeble 1500, which was utilized in the research we'll be talking about today. So our Gleeble 1500 has been in the labs since for nearly 20 years. It's been as upgraded as we know how to make it, with digital control for thermal and mechanical systems. We have some accessories, including a C-gauge dilatometer. We have an older quench system, and the primary types of studies that we perform would, in the last 4 to 5 years, would include things like metallurgical phase transformation, characterization. There's some work that came out from my group earlier this year focused on supermartensitic stainless steels. I'll refer you to the paper down here. We've also looked at simulating welding fusion zones, in particular looking at how we can couple welding to the Gleeble experiments, and that's what I'll be talking about today. And then we have a number of experiments, ongoing work on looking at simulating welding heat affected zones using this equipment. So we endeavor to keep it in calibration and so that it's available and ready for research. And it's a great tool, and we're glad that we have it. So with that, let's move on to the technical part of the talk today. So our focus is on describing the coupling of welding experiments with these Gleeble thermomechanical simulations. And we're going to be speaking specifically about duplex stainless steels, and so I'd like to just give a little context before we dive into that. So duplex stainless steels are a mixture of austenite and ferrite, and what I present here is a representative micrograph of as-received base material showing this rolled microstructure. In this particular case, the austenite is etched the lighter phase here. It has excellent corrosion resistance and toughness, high yield strength depending upon the specific grade, and service temperatures from -40 to roughly 280 C is the upper limit. The corrosion resistance is the prime benefit for these materials over, for example, austenitic stainless steels. Greatly improved chloride corrosion resistance, so finds applications in places like offshore, petrochemical piping, pulp and paper. Typical alloys are two common ones are indicated here in this table, and you'll see that these are iron, chrome, nickel systems with a notable addition, intentional addition of nitrogen. So, of course, nickel is an austenite stabilizer, and nitrogen is intentionally added as well, and it also stabilizes austenite. The 2205 grade has 65 KSI minimum yield, and you can see the representative compositions here. The so-called super duplex 2507 goes to higher yield strength as well as improved corrosion resistance due to the additional degree of chromium, nickel, and moly, as well as nitrogen. Conventionally, these materials are ranked by their pitting resistance equivalent number indicated here, and so-called super duplex stainless steels would have a PREN over 40. Digging into the physical metallurgy in a little bit more detail. So all duplex stainless steels will solidify from the liquid as ferrite, and upon further cooling, this fully ferritic microstructure will enter a two-phase regime in the phase space where austenite will begin to nucleate from ferrite grain boundaries, and in some cases may form these Beedman-Staton or side plate morphologies. This is an example of a cast type structure reported by Ganeri et al. From a laser weld fusion zone, and depending upon the cooling rates, if we have fast cooling rates, we will tend to suppress the nucleation growth of austenite and will result in a ferrite-rich microstructure, such as one sees here. In this case, the austenite etches light. So the cooling rate has a big effect on the austenite volume fraction, and slow cooling, if between 475 and 850 C, and what constitutes slow depends upon the specific composition, may promote the formation of brittle intermetallics such as sigma phase. So the time temperature history of these materials is quite important for microstructure control and property control. When thinking about reheating a duplex microstructure, in some alloys we can get complete transformation to ferrite above the ferrite solvus temperature. However, in some alloys they may not be able to fully transform to ferrite even up to the solidus temperature, such has been reported by Ramirez et al., for example, in the 2507 type alloy. It's also known, as has been reported by Lippold and Katecki, Ramirez et al., that reheating can promote secondary austenite formation, called secondary because it's forming under reheating. Bottom line is that controlling phase balance, and our typical target would be 35 to 60% ferrite, is really important to achieve our desired toughness and corrosion resistance for these materials. So if we think about weldability then, in a typical wrought or rolled type plate, we would see this sort of microstructure with a balanced ferrite and austenite phase. And our target and ideal properties would be, in this case, of 50% austenite, 50% ferrite. Now, the welding process variables must all be engineered to achieve this 35 to 60% ferrite in the fusion zone and the heat affected zone. Now, of course, this will depend in great detail upon the composition of the material, which will drive the kinetics of the phases that form, the welding process conditions, such as heat input, that control the cooling rates, and then finally composition. So all these details must be considered in order to achieve the target microstructures. Thermal history is known to be important, as I've already mentioned, about the potential to drive secondary austenite formation. As we look at a representative micrograph from our work, you can see that at this boundary between the fusion zone, heat affected zone, and base metal, we can see profound changes in the microstructure. The base metal is distinguished by this wrought, rolled type microstructure. In this particular alloy, the 2507, because of the suppression of complete transformation to ferrite, the heat affected zone actually tends to be quite narrow, which is beneficial. And then you can see the presence of austenite, which etches in the lighter phase here in the fusion zone. So with this as a background, let me go ahead and state what we were trying to do in this work. So we had two major research objectives. So the first was a kind of exploratory study where we were looking at correlating heat input of multi-passed welds to microstructure. And in so doing, we got some unexpected results. And that drove the second phase of the work, where we tried to test some hypothesized mechanisms. And we found that the thermomechanical simulations, coupled with welding, were really key and helpful in driving or identifying the key drivers and isolating those. So let's begin. So in the first experiment, we used a standard 98% argon, 2% nitrogen shielding gas, conventional arc parameters, using a mechanized gas tungsten arc welding process and a 75-degree included angle joint design, as indicated here in the picture. We designed these welds to run in three major ways. The first was a high heat input weld with 2 passes, then a mid-range 4-pass weld, and then a low heat input 6-pass weld. And our goal was to understand how the microstructure varied with process parameters. We focused in particular on the root pass under the idea that this would likely be the location that might be in contact with a corrosive media. And what we found was a somewhat unexpected result. So in our first findings, we looked at the microstructures for increasing arc energy, and what we saw was opposite of what we expected. From the literature, we expect that high heat input will result in slow cooling rates, which ought to result in higher austenite contents. But we found exactly the opposite, and this was the beginning of our starting point for the rest of the study, to try to understand why it is that we see so much more austenite in the root of the pass. We plotted the percent austenite as a function of arc energy. We found almost a linear decrease, and we know from the literature, as I've already alluded to, that it's suggested that reheating is a prime driver for causing secondary austenite to form. And so this led us to hypothesize that perhaps that was the driver. When we looked at this in terms of the number of welding passes, it began to sort of fit within this prior known work. And you can see that as the number of welding passes increases, we see this increase in the percent of austenite in the root of the pass. So zooming in and looking at one of these 6-pass welds that have the higher austenite content, we can see these small amounts, these small and very prevalent amounts of intergranular secondary austenite formation. And so this led us to make the following hypothesis, that a higher number of passes are resulting in thermal reheating of the fusion zone root pass, which is causing the secondary austenite growth and overall increase of austenite volume fraction. So to test this hypothesis, we wanted to really dig into it, and so we designed the following set of experiments. we performed a root pass and then embedded a thermocouple up through the backside. We then proceeded to weld that, measure the in situ temperature response in the root pass, section the weld, examine the microstructure, followed by a third pass where we did the same, and then finally a fourth pass. This allowed us to begin to directly correlate time temperature profile, peak temperatures, and the actual austenite volume fraction in the root pass. Here's what we found. Here is our starting root pass microstructure. Using image analysis, binary thresholding, and segmentation, we find nominally 43.5% austenite, as you can see here. As we add the next pass, you can see the thermal cycle here. We find a peak temperature of roughly 1200 degrees C, and we can see that the austenite volume fraction increases. So we've now terminated the experiment, sectioned this weld, and now we're measuring the austenite volume fraction here. Continue the experiment, do the same thing. We find the austenite volume fraction increases again. And then finally, we do the final and find that within the uncertainty, it's about the same, or perhaps it's decreased just a little bit. All of these passes have peak temperatures between 800 and 1200 degrees C, which is the range in which it's known to drive secondary austenite formation. So this all seems quite telling. As we look at plotting the austenite fraction as a function of the number of passes, you can see that it's maximized with the third pass before it dropping slightly in the fourth pass. If we go through and just characterize the austenite content through position in the weld, we appear to find, consistent with this, the highest is in that second pass. It's unclear, perhaps this is driven by dilution effects from the surrounding base material, but the key point to take away is that these thermal cycles appear to be driving the microstructure evolution in the weld. So to understand the role that composition could play, we wanted to isolate the role of nitrogen stabilizing in these argon shielding gases. And so to do that, my students came up with the clever idea that we would make multiple bead-on-plate welds in 1/8 inch thick. So this is a single pass, penetrates all the way through the plate, but then vary and control the shielding gas content, and then use these for subsequent in situ reheating using the measured thermal response that we obtained in situ from the weld. And so now we can directly probe the degree to which composition is a factor as measured through the surrogate nitrogen content in these shielding gases as opposed to thermal cycle. And so here's the results. They performed all of those series of experiments, and with these 3 different levels of shielding gas. And in case 1, 100% argon, you can see that we do have lower amount of austenite in the root, while as we increase our nitrogen shielding, we do increase our starting austenite content. Now, as we apply the same thermal cycle, you can see in all cases, we begin to grow the secondary austenite, which continuously increases with these application of the 3 thermal cycles that were directly measured from the weld. So, plotting the results. In figure A here, we plot the austenite volume fraction for the 3 different levels of shielding gases as we increase the number of reheating thermal cycles. And significantly, from a practical standpoint, we see that the third reheating cycle, by the time that we get to that, there is effectively negligible difference between the 98.2 and the 94.6 shielding gas, which is consistent with industry recommendations to use the 98.2 shielding gas. There is an increase in austenite, it appears, relative to the 100% argon. And in this plot, figure B, we just plot this as a function of the nitrogen shielding gas content, which yields effectively the same conclusions. So as a final experiment, we performed a 14-pass welding experiment using a 1/2 inch plate, where we took a similar kind of approach. We embedded a thermocouple for in situ root pass temperature monitoring, And then we did two things. The first was we plot the peak temperature as a function of these reheating thermal cycles. And significantly, what we find is that by the time one exceeds 5 reheating thermal cycles, one falls below this peak temperature of 800 C. Now, we then took a cross-section of that and we did the austenite volume fraction characterization as a function of the pass number. So, for example, pass 0 would be the root pass, and it corresponds to 14 reheating thermal cycles, while pass 14, which would be the cap pass, would correspond to the as deposited. So first, let me highlight the black. So increasing the number of passes, we're just going up through the position of the weld, and notably, with the exception of this outlier, which had dramatically different microstructure, and we consider it non-representative, not exactly sure why, but not a representative data point. The key point is that as we move up through from 0 to pass 8, all of these have a minimum of 6 reheating thermal cycles. The austenite volume fraction is effectively constant. However, as we get towards the cap of the weld, we see that the fraction of austenite falls off. Now, in this particular case, because we're using the 98.2 shielding gas, we're using a slightly over-alloyed nickel content. We are at the 50% austenite volume fraction there in that cap pass. Just for comparison, I plotted here the results from our 4-pass weld, and you can see that we're getting good and decent agreement. And so what we see is that these reheating thermal cycles really do appear to correlate. It's driven by this peak temperature. Total time above this 800 C is critical, well in line with the older literature, such as Ramirez et al. And you can see that the results kind of all fit together. So just to wrap it up today, clearly the key takeaway from all of this is that heat input is really important for microstructure control. However, just thinking solely in terms of heat input, if you're doing multiple passes, we need to think about the impact of these reheating. And this is all consistent with previous reports. And if you really want to dig into the details of the mechanisms of secondary austenite growth, which has been well explored by Ramirez and colleagues in previous work. And then finally, in line with industry practice, clearly the 2% nitrogen shielding gas is acceptable. So to finally conclude, the initially surprising welding results when we dug through all the details were consistent with previously reported mechanisms. It's clear that reheating is driving the secondary austenite volume increase due to the formation of intergranular secondary austenite. Total time spent in this critical 800 to 1200 C temperature range is important for increasing the austenite content. And we really do need to bring all of these factors together, chemical composition through nitrogen gas additions over alloyed nickel filler wires, arc energy, and of course these thermal cycles to really understand how microstructure evolves. And finally, we showed that using the Gleeble, we were able to couple not just Gleeble for base metal evolution, but to actually bring in these welding bead on plate experiments to actually directly probe how both composition in the form of the nitrogen shielding gas content and the thermal history drove the subsequent austenite volume percentage. I do want to acknowledge a number of folks, the core team, Tim Pickle and colleagues who were the key students who did this work. It's been reported in the Welding Journal. Also want to thank a number of several other students who contributed at various points to this work. Bechtel was an early partner that supported work for several of these students over one summer that got all of this going before it was carried on just in the context of a senior capstone project. We're grateful to Otokumpu and Voestalpine Buller for material donations. Arc Specialties, multiple years ago, brought in this gas tungsten arc mechanized welding equipment, and then a number of folks provided useful discussions along the way, and we acknowledge and thank all of them. Finally, I'll just direct you to some of the literature. If you want to learn more, of course, classic works on just general duplex steel weldability issues by Messer and colleagues, as well as the textbook by Lipolo-Kotecki. The mechanisms of the secondary austenite formation, I refer you to the work by Ramirez and colleagues. And then finally, if you want to read more of our own work, I'll direct you to these 2 papers in the Welding Journal. The work I've described today is really focused in this paper here, and then collaborators have done more work probing nitrogen and its role, and so I refer you to that work here. Finally, I thank you for your attention and would be delighted to answer any questions. Thank you very much.